In the past few videos, we've looked at oscillations in one dimension. And now, quite obviously, oscillations can take place in higher dimensions as well. This should be particularly clear since we've just shown that oscillations can take place around any minimum in a potential function. And clearly, a potential function can have a minimum in 2 dimensions and 3 dimensions as well. So what we're going to do here is study oscillations in 2 dimensions. A few new things happen when you go to higher dimensions. The more interesting ones we're going to save until the end of the semester when we talk about coupled oscillators. But we will start to introduce the subject here and allude to some of the things we'll study later. So let's say that we have a 2-dimensional potential that looks like this. It's essentially an isotropic potential, in that it looks the same in all directions. Basically, the energy depends only on the distance of the origin, r, not on the direction. And you can write that then as 1/2 k times x squared plus y squared. This, you should know that if we take the gradient of this, then we get directly that f of x equals minus k times x, and f of y equals minus k times y. Another way to write that, if you like, is to say that the force is minus k times the vector r. So again, the force points towards the origin along the direction of the vector r. So if we now apply Newton's second law, we'll find directly 2 decoupled equations, because the motion in x depends only on a force that depends only on the position in x. We get x double dot equals minus k over m. X and y double dot similarly is minus k over m times y. And we can quickly solve that, and we will find so we have 2 independent equations here. Oh, and of course, omega is the square root of k over m. So we have 2 independent equations over here, and that gives us the 2 independent, completely decoupled solutions in x and in y. Now, when we do this, we are choosing phi of x and phi of y any way we like. Those are the 2 phase angles. But by choosing the origin of time, we can pick one of them to be 0. So let's choose t equal to 0, such that phi of x equals to 0, and then we'll also take that phi is phi y minus phi x. And then to simplify slightly, and we'll get that x equals a times cosine of omega t, and y equal ax times cosine of omega t, and ay is, and y equals a sub y times cosine of omega t minus phi. So that's the most general solution in 2 dimensions for an isotropic potential, provided that we choose the origin of time such that x starts out at its turning point. Okay. Now, it turns out that the choice of phi here has a strong effect on the trajectory. So we're going to look at that next. So we're going to consider the particular cases, first of all, of a sub x equals 0, or a sub y equals 0. Not both, of course, because then you have no motion at all. Then we're going to look at phi equals 0, or for that matter, pi. And then the third case we're going to look at is phi equals pi over 2 or 3 pi over 2. Or minus these values. That works too. Now, if we look at the solutions here, we can see that what kind of motion these corresponds to. If a of x or a sub y equals 0, then we have motion only along a coordinate axis. Only one of the oscillators is moving. If phi is 0 or pi, in this case, I'm going to look at that specifically over here, then we get that x equals ax cosine of omega t, and y equals ay also cosine of omega t. So that's really ay over ax times x. So y is proportional to x. So this gives you a straight line. Just like in this case, only that this line is not going to be along a coordinate axis. The final case will be this one. We consider that over here. So under those circumstances, well, if you have phi equals pi over 2, so cosine of something minus pi over 2, that's sine of something. So in this case, we have that x equals ax cosine of omega t, and y equals ay sine of omega t. And if you look at this a little bit, you can see that this is actually motion along an ellipse. For other values of phi, motion, as it turns out, is also going to be an ellipse. It's just going to be a little bit tilted. Okay, so just to show that this is the case, I have prepared a Mathematica program, which we're going to run now. So this is it. Up here we have the potential of the in x and in y. These lines here are equipotential lines, and we're going to plot the trajectory of the oscillator here. So this is a two-dimensional plot. It's sort of like the phase plot that we showed a couple of videos ago. The difference is that this one is in x and y, not in p and x, not in momentum and position, but just two position directions. The full phase plot for this oscillator, because it's in two dimensions, will need to include two momenta and two positions, and it will be four-dimensional. Since I don't have a four-dimensional display, and I think you probably don't either, we're going to have to make some choices of what we actually display, and in this case we're going to show y versus x. On this plot we'll show just the motion in y versus time, and here we'll show the motion in x versus time. So let's look at the different cases that we have here. So first we said that, okay, either a of x equals 0 or a of y equals 0. Well, that's really the same thing as taking the energy in the x direction or the energy in the y direction to be 0. So I'm going to set the energy along the x-axis to be 0. And if we then run the oscillator, then we get motion only along the y-axis, just like I said. That makes sense, right? So this seems to be working. We can then reset that, and then we'll do motion only along the x-axis. That's what that looks like. All right. Then we'll have phi. I have phi over here. It's 0 times pi. If it is 0, then our solution should tell us that we move along a straight line no matter what energies we pick. So we'll just pick some random energies, and then we'll run this here. So we have oscillation in y and we have oscillation in x, but they're both perfectly in phase, and therefore we're moving along a straight line. If I pause that here, you can see that the phase of the motion in x and in y are the same. Okay. And then we will take the case of phi equals pi over 2. Oh, that was the wrong one. This is phi. That's pi times 1/2. That's pi over 2. And then we'll run the oscillator. And just like we predicted, this is an ellipse. The size of this ellipse depends on the energies. If we take the energies to be the same, we're actually moving in a circle here. So this oscillator now has constant potential energy and constant kinetic energy, because it's always moving at the same velocity at the same potential line. So that's something you can have in one dimension, but it's certainly possible to have in 2 dimensions. Okay. Then finally, we'll just look at some random case. So we'll take phi, this angle, to be anything we like, and different energies here. And then we'll run it. And again, we get an ellipse, although not one that's oriented with its major axis along either x or y, but we get elliptical motion nonetheless. So those are the different kinds of motion we can have in the isotropic case, which means that the force is proportional to the vector r, and that the potential itself is perfectly isotropic. We can see here that these are equipotential lines. They are circles. Now, this program also allows us to change the strength of the potential in different directions. So we can, if we like, have different oscillation strengths in different directions, so that the oscillator is no longer isotropic. And that's what we're going to look at next here. So an anisotropic oscillator corresponds to different spring constant in different directions. So let's look at the anisotropic case. So that means that in general you will have potential as a function of x and y that looks like this, which means that we have and that still gives us 2 uncoupled differential equations. But we have 2 different omegas here. In the last case, we had the same omega both in x and y. Here it depends on the spring constant, which varies in the 2 different directions. Okay, so this gives us then, in general, where again we've chosen the convention that the oscillator in the x direction starts at its turning point when the time t equals 0. So let's look at what that looks like in Mathematica. So now I have different omegas in x and y, so I can change them here. So let's begin with taking omega in the x direction to be, let's say, 1, and omega in the y direction to be 1.5. So you have a nice ellipse here. We'll keep phi at 0 degrees for now, and then we'll run the oscillator and see what happens. So we still have, in the y direction and the x direction, nice oscillatory behavior, but the oscillator itself, as it's moving here, is not moving along a particularly simple curve. It has this knot shape, and what that knot shape looks like changes depending on exactly what choices we make, both for the initial conditions and for the frequencies. So for instance, if I pick a different initial angle here, different phi, I get a different behavior. Right? In fact, this is smart enough that I can change this while I go along. Right? And I can change the energies here too. That doesn't change the shape, but it does change the aspect ratio of this figure that the oscillator writes out. And depending on what I choose here for my frequencies, things get more and less complicated. So now here we had a ratio of 3 to 2 for the oscillator frequencies. We can try other things here. How about 3 to 1? What does that do? Well, so that's what that looks like, depending on the phase. Okay. How about two that are pretty close to one another, like 1.75 and 2. So now we have omega x equals 2, omega y equals 1.75, and I've chosen here phi to be 3/16 pi. And we'll run that and see what that does. So that's a significantly more complicated pattern, but just like the pattern that we saw before, it repeats. It returns back to where it was before. It traces out the same trajectory that it had when it started. We can run this forever, and basically this is what the trajectory looked like. It's closed. Okay, so the question is, do we always get that? Well, what characterizes these numbers here, 2 and 1.75, is that they are rational. So let's try something else here. Let's say that omega x is square root of 2. Can't tell here, but this is actually square root of 2. It doesn't end after this, it continues. And we're going to pick omega y to be 1.25. And we'll take an original angle of, let's say, 11/16 pi. Let's see what that does. So these longer times we're getting some roughness here. This is just because mathematically it's plotting a finite number of points, and that's why it looks like that. It will go away once the evaluation stops. So that's what we get. So this looks interesting. It looks almost like we would visit every point here, more or less. This looks more or less completely filled in. Depending on what we pick here, we can make it look even more filled in here. 9/16 pi. Looks almost completely filled in. That's different from what we saw when these numbers were just integers or could be made up by fractions. Now we have a square root here, and that actually makes a difference. It turns out, in fact, that if the ratio of omega y to omega x is a rational number, that is a ratio of two integers, then the trajectory of the oscillator repeats. It comes back to its original configuration. Otherwise it doesn't. If it's irrational, then the oscillator eventually visits every point, or at least comes arbitrarily close to every point that's within this rectangle here. So let's take a minute or two just to prove that. So what we just said was that, let's draw a little line here, that if omega x over omega y is rational, that is, if you can write it as some integer n over some integer m, then the trajectory repeats. And otherwise it doesn't. Okay. So to prove it, let's assume that it is rational. If we can write omega x over omega y as n over m, that means that we can write n over omega x as m over omega y. Now let's pick a time, t, such that 2 pi n over omega x. So the time is 2 pi times n over omega x. We're perfectly able to do that. Now n over omega x is m over omega y. So this is also equal to 2 pi m over omega y. And then we'll use that time. Let's see what we get here. I'm going to call this t prime, perhaps. So x of t prime equals a sub x times cosine of this time here. So we have omega x times 2 pi n over omega x. So omega x cancels. We get cosine of 2 pi n. Since n is an integer, that's the same as cosine of 0, which is cosine of omega x times 0, for instance. So that is x of 0. That's the original position and configuration, right? And same thing for y prime, or y of t prime. Although now I pick this version of that time. So, if we can write this, then it repeats, right? Then the trajectory gets back to its original position. If not, if we can write it this way, well, then the trajectory will actually never come back to its original position. And we have this complete filling of the phase space that we just saw. So let's look at that again here. Right, so your phase space is completely filled. I should note that this, I'll run for a little bit, that this is not chaos. Right? Chaos looks similar when you look at it in that you have motion that tends to fill up all of phase space. But if you look at the motion in y and the motion in x, it's perfectly regular. So chaos is something different from this, and we will actually treat that a little bit, just a touch of it, next semester. The other thing that one can do here is to look at different kinds of potentials. The potential that we used in this case, let me make some more room for it here. The potential that we were working with was ux equals 1/2 kx x squared plus 1/2 k sub y y squared. Okay, so that's the potential. If you look here, it's shown by these equipotential lines. I'll take this away so you can see it more clearly. So they are ellipses. Now, nothing says that these ellipses have to be oriented along the coordinate axis. We can actually tilt this if we like. It's perfectly okay. Let's take a slightly larger ratio there to make it more clear, right? So I can tilt this any way I like. It's perfectly a fine potential. The difference is, though, that when you do that, we're not going to be able to write this as something times x squared plus something times y squared. The differential equations that we end up with are going to be going to couple x and y. So when we let's go back to zero angle here. So if we were to look at what this looks like here. Now this is a rational ratio again. So we get this repetitive pattern. Let's pick that one. So it repeats. And if I rotate the potential, then obviously the pattern rotates too. But we can see here, though, that the motion in x and y no longer looks as simple as it used to. It's no longer simple cosine and sine motion. And this becomes more clear if we do this at higher frequencies. Like this. Right? Here we have something that doesn't behave like a simple sinusoidal motion anymore. This is something that we're going to treat at the end of the semester when we talk about coupled oscillators. The situation will be slightly different then, but it will actually be completely equivalent to what you're seeing here. So I'm going to end this video now with a question for you. If we turn this back to the rotation, we can see here that no matter what omega x and omega y that we choose, the oscillator explores an area that is a rectangle. Now, if you think about it, that's a little strange, right? Because the energy of the oscillator is a constant, and constant energy here corresponds to these ellipses. So, for instance, this oscillator at these settings that I've chosen here could explore anything that's inside this ellipse that I'm tracing out, in principle. But it doesn't. It restricts itself to this rectangular area. So the question I'm asking you, and that I hope that you'll be able to answer in class next time, is why is it that the 2D harmonic oscillator's motion is restricted to a rectangle in 2 dimensions and not an ellipse, like you'd think if you just made a simple energy argument? So we'll end here, and we'll discuss that in class next.